Use the source.
Okay, we're finishing chapters 8 and 9 here, the notes from that, on what I call section B, exponential growth. And so we already talked about linear growth, now it's time for exponential growth. Just a reminder, linear growth, it's when you add something or subtract for every unit of time. You know, so that's how you get paid $12 per hour, so every hour you add another 12. Exponential growth is different though. Exponential growth is when you multiply or divide by something every time. And so a little bit different scenario there. So let's remind ourselves a little bit about multiplication and percents. So remember, if you say something increases by 12%, you can multiply the original amount by 1 plus 0.12, and that would get you the new amount. So if you just multiplied by just 0.12, that would get you the amount you add, and then you'd have to add it back to the original. So this 1 here accounts for adding back the original. So remember that. Same thing if you want to multiply or if you want to have a decrease. So here's a 12% decrease. So you're going to multiply by 1 minus 0.12 because it's a decrease. So a new amount would be equal to the old amount times, in this case, 0.88. All right. And so just a little quick review. That's going to become vitally important here, and we'll see on the next page. So let's say you have $100 and each day you get 2% more. So after 0 days, you have $100. Nothing's happened. After 1 day though, because you get 2% more, that's a multiplication idea. That's a change due to percents. And here you go. Here's that 1.02 like we just talked about on the previous slide. And that gets you $102. Now after a second day, you're going to multiply by 1.02 twice. Once for the first day, once for the second day. And that is like saying 1.02 squared. And that's a short way to do that formula. Third day, there's 3 of them. You notice it's cubed. Fourth day, there's going to be 4 times you multiply, and so that's to the 4th power. And after n days, you're multiplying n times, and so we have an nth power here. All right, and that's the idea of exponential growth. It's this continual multiplication. So if we look at that last formula, right, where'd the 100 come from? That is your starting amount. All right, or we could like to call that the initial amount, right? 1.02, well the 1 is always for the original, and then the 0.02 was, we added the rate, so that came from the rate. And the n, well that was the number of times we multiplied. In this case, it happened to be days. Okay, so that brings us to this formula. So exponential growth formula, again, the Q's are for quantities. That's why we use Q. And remember, Q sub 0 here, that is Q, or the quantity at time 0. Okay, so you're starting quantity. R is your rate. It's a percent, and it's what percent you are adding and subtracting. Remember, this needs to be a percent as a decimal. We always use we always turn percents into decimals when we do arithmetic. And then this is a power up here, and that's a t power. And just like with linear, your units must match here. Okay. If you're decreasing, your R value is negative, right? Because you have a negative R value for decreasing, and so up in the formula, it's actually going to be a 1 minus R. So let's take a quick look here. Let's say you weigh 189 pounds, and if you lose 3% of your weight per week, we could model it like this. The quantity, in this case your weight, starting weight, starting amount, 189. You're losing 3%, so that's a decrease. So minus 0.03 and to the t power. And so we could simplify that equation. That would be 0.97 to the t. And what is t here? Well, it's 3% per week, so t is in weeks. Just like with the linear, we like to remind ourselves, what does that t value represent? All right, so here's a little bit of a graph to help you understand the difference of the linear versus exponential. Linear, you're adding every time. So in this case, straight town, so conveniently named. Linear always is a line, creates a line when you graph it. So straight town is a straight line in the graph. Ha 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 ha. So here's straight town. You're adding the same amount every time, so it's a linear growth. Okay, a line. Exponential though, you're multiplying every time, and every time you multiply, you're multiplying by a bigger amount, multiplying by a bigger amount, multiplying by a bigger amount, and so it grows much, much faster. Okay, and a lot of times when we talk about exponential growth, we are very concerned with doublings of the pattern, and we'll talk about doubling time a little bit later. Another example of linear versus exponential. Talk about simple interest and compound interest, which was in the financial chapter, chapter 4. So at 10%, 10% of 1,000 is 100. So with simple interest, that's the same amount you add every time. So plus 100, plus 100, plus 100, plus 100. That's linear. So this is a very linear growth. You add 100 every time. Compound interest, though, you multiply every time. So we're going to multiply by 10%, multiply by 10%, multiply by 10%. So that's why this keeps going up, because 10% of your newer value, it keeps getting bigger and bigger. And so compound interest is exponential. All right, and if you can see here, here's the compound interest formula. A equals P times the quantity of 1 plus R over N to the NT. So it's very much like the formula we just looked at a second ago. P is your starting amount. That's your starting balance in the compound interest formula. 1 plus R over N. Why R over N? Because you're adding the percent for each term. So the percent gets divided up over each term. And then NT, because that's the number of times that's happening. So compound interest really is this exponential formula idea. It just has a few extra parts in it, mainly the N, because the N affects the time or the term of everything. All right, so let's take a look at this example. You're given a choice to take $1,000 each month for the rest of your life, or be given a magic penny. The magic penny will turn into 2 pennies after 1 day, then double again into 4 pennies the next day, and so on. Which option would you take? Well, let's just look what happens after 30 days. Well, if you get $100, let's see here, take 1,000 each month. Oh, 1,000 each month. So that would be a linear. You're adding 1,000 every month. So we would use the linear equation here. There it is. You start with nothing, and your rate's 1,000. And if I did this after 30 days, we'll say that's 1 month. So after 1 month, you have $1,000, right? Okay, how about the penny, though? The penny is exponential. You're multiplying. You're doubling it. All right? So if you're doubling, by the way, doubling is 100% increase. So 100% as a decimal is 1. So you start with a penny, starting amount, 1 plus R. Again, R is 1, because it's 100% increase. And T, well, R is it's a doubling every day, 100% increase per day. And so 30 days is my T value here. And so if we work that out, that's 0.01 times 2 to the 30th power. That is, holy cow, looks like $10 million, almost 11 million. So this power of exponential growth is really good in terms of investments and everything. Your investments grow with compound interest, and that exponential idea really helps things grow fast. And so you like that. So let's try some other examples. Bacteria in a bottle. Suppose you put a single bacterium in a bottle at 11 a.m. It grows, and at 11:01 it divides into 2 bacteria. These 2 bacteria grow, and at 11:02 divide into 4 bacteria, and so on and so forth. Okay, so write an equation modeling the number of bacteria. So just a reminder, it's exponential. And I know it's exponential because you're not adding something every time, it's doubling. And doubling is a multiplication effect, so exponential. So Q equals, well, how many bacteria did I start with? I started with 1. And 1 plus R to the T. What's my R? Well, remember at 11, you had 1 bacteria. At 11:01, it doubled to 2. At 11:02, it doubled to 4. Then up to 8, so on and so forth. Well, to go from here to here is 100% increase, just like with a penny. And 100% increase, this is 100% increase. In other words, you added 100% of 2, which is 2, to 2, and you got 4. So how do you model 100% increase? That is an R of 1. And so my R value is 1 here. So we can change this equation into 1 times 2 to the T, and then you can even simplify. You don't need the 1 out in front. The quantity here is just 2 to the T power. All right, let's try another. Okay, let's look at this example. The world population doubled from 3 billion in 1960 to 6 billion in 2000. Keyword there, doubled. That's a times 2. That's a multiplication, so you should think exponential. What would the so suppose that the world population continued to grow from 2000 on, so from the year 2000, with a doubling time of 40 years. What would the population be in 2050? So reminder, doubling time means 100% increase, and this is happening every 40 years, by the way. But 100% increase means R is 1. So that gives us this equation. So R is 1. Where'd the 6 come from? Well, the 6 is the population in 2000 because they wanted us to talk about this growing from the year 2000 on. So my model is built from 2000 on. All right. The 1, that's the R. Where'd the 40 come from? Well, the double, we double our R value happens over 40 years. It doubles every 40 years. So T is in years, but the doubling or the R value is per 40 years. So we had to divide by 40 to make our time match this per 40 years idea of doubling. And also we should make a note, because this was in 2000, T is what? T is years since 2000. All right. So there's our equation. And if we plug in 50, because in 2050, that is 50 years since 2000, then we get 14.27. And remember, since 6 is in billions, my final answer is in billions. Also, if you type this in your calculator, this whole thing's the power. So make sure that whole power is in parentheses. If it's not in parentheses, you'll get it wrong. Okay, let's look at this one now. China's rapid economic development has led to an exponentially growing demand for energy, and China generates more than 2/3 of its energy by burning coal. During 1998 to 2000, China's coal consumption increased an average of 8% per year. In the 2008 consumption was about 2.1 billion tons of coal. Use these data to predict China's coal consumption in 2028. So it said that it was exponential. What's my starting value? So it's got to be an amount of coal. Well, the only amount of coal I have is this 2.1 billion tons. So 2.1, and I'll just know that our quantity is in billions. And then it's times 1 plus R, 8% per year, so that's 0.08. And it's per year, my T is in years. However, 2.1 happened when? In 2008. So my T is what? Years since 2008. And so now if I want to know how much was in 2028, that means 2028, my T value is 20, because it's 20 years after 2008. And so if we plug that in, 2.1 times 1.08 to the 20th power, and I believe you get 9.79. But remember, our initial amount was in billions of tons, so this is also billion tons of coal. Okay, here's another one. When doctors prescribe medicine, they must consider how much the drug's effectiveness will decrease as time passes. If each hour a drug is only 95% as effective as the previous hour, at some point the patient will not be receiving enough medicine and must be given another dose. So A, if the initial dose was 250 milligrams and the drug was administered 3 hours ago, how much is left? Okay, well, it's exponential, and you know that because there's a percent involved, and if we have percents, percent increase, decrease is a multiplication, yeah? Initial dose, 250 milligrams. Now, it's 95% as effective. That's like saying it has a 5% decrease. So 1 minus 0.05 and to the T power. And what's T? 95% as effective as the previous hour. So a decrease of 5% per hour. So my T here is in hours, by the way. Now notice if I simplify that, 0.95. Okay, and that's not a coincidence. That makes sense. If you're 95% as effective after an hour, there's 95% as much left. So that's what this equation is telling us. But I wanted to make sure we understood the proper R value. Okay, so how much is left after 3 hours? We'll plug in 3 for T. And what do you get? I believe you get 214.34 milligrams. Okay. B says if the drug is ineffective when below 52 milligrams, should the patient be given another dose? Well, after 3 hours, we're well above 52. So do they need another dose? That would be a no. Some key facts about exponential growth. Exponential growth leads to repeated doublings. So because of this multiplication idea, eventually there's a doubling, and then there's another doubling, and another doubling. However, you got to realize that exponential growth cannot continue forever. After only a few doublings, quantities reach impossible proportions. You know, if you think of population, eventually we're going to run out of space and food. There's not going to be enough land, not enough food, not enough energy. So population does grow exponentially. There are exponential models for it, and they're pretty accurate. But it's not going to be able to go on forever and ever. So great models, but there are some limitations to them. Another common growth idea with exponential growth is cancer. A lot of cancer and bacteria and things like that, biological things, they tend to grow in an exponential fashion. And so one of the things we concern ourselves about cancer is the doubling time, and trying to figure that out. Likewise, lots of things have an exponential decay, and so we look at the half-life or halving time. How long does it take to be cut in half? All right. And so we're very concerned when those things exactly happen. So to find that out, we have this formula here. Now, don't let this formula freak you out. T sub double, so that's doubling time. It's log. So log is a button on your calculator down here. You see it? It looks like that. You should have that somewhere on your calculator. Just think of it like the square root button. Log has something to do with finding powers and in a square root kind of idea. We're not going to go in and learn all the tricks of that, if you will. But just think of it as like a square root button, okay? You guys don't know how to calculate square roots by hand. I would never make you do that. It's the same thing with logs. Logs, it's a math thing. It's too much of a pain to calculate by hand, so we have a button for it. Okay, so just think of it like that. So you take log of 2 and you divide it by log of 1 plus r. And r, again, is your percent as a decimal. Now, if it's decreasing, then it has a half-life. All right, in other words, how long does it take for this thing to be cut in half, if you will? And the formula here is that there's a negative out front, log of 2 over log of 1 minus r, and r is your percent. Okay? So those are those two formulas. Just keep those in mind. So as an example, if you had an account that had a compound interest rate of 5% per month, how long would it take for your money to double? Well, if you use the doubling time formula, it's log of 2 divided by log of 1 plus 0.05, because my rate is 5%. And if you calculate that out, you should get 14.206. Or I could show you remember we call this an amortization schedule. And here it is. Notice that between the 14th and 15th month, our money doubled. And this actually does not matter what your initial amount was. You notice I never said what your initial amount was. In my chart here, I made up an initial balance of 1,000, but that does not matter. If you know your growth rate as a percent, it does not matter what the amount is. You can always figure out the doubling time regardless of your initial amount. Same thing with your half-life or halving time. So let's do an example here. What is the exact half-life time? You have an urban encroachment is causing a forest to decline at a rate of 4.25% per year. So let's put it in that formula. Minus log of 2 over log of 1 minus 0.0425. So 4.25% as a decimal is 0.0425. You work that out, and it's 15.96. 15.96 what? Well, my rate was per year. So here's your years. So in other words, this forest is going to be cut in half. It's going to be half as big in about 16 years. All right. If the forest in that local area started with 500,000 acres, how much will be left in 20 years? Well, that again is just this exponential growth idea. You got a new value, or your Q is your initial amount times 0.05. Where'd 0.5. Where'd that come from? Well, 1 minus, it's halving. Halving is cutting by 50%. So your rate is a 50% cut. So 1 minus 0.5 is 0.5. And then 20 years later, y divided by 15.96. Well, because you're having here, your 50% decrease happens every 15.96 years. And so if your rate is happening per some time period, your time here must also match that. All right. And so if we started in with 500,000 acres, that's going to give us 209,000 acres after 20 years. And over here, I showed you how I typed all that in the calculator, so that can help you out. By the way, that yellow box there, that represents about 209,000 acres, just to give you an idea. So over the course of a 20-year period, this city in this example is growing so much that it cut out a forest about the size of that yellow box. Okay. All right, let's do another one. A community of zombies starts with 3 zombies and doubles every 6 hours. What is the doubling time? Well, in this case, I told you, it's 6 hours. Okay, nothing to calculate there. Write an equation modeling the population. Well, it's Q equals the initial amount of zombies was 1. A doubling is 100% increase. And so R is 1. And so when you have in the formula 1 plus 1 to the T, but your doubling is measured doubles every 6 hours. So we got to divide our T by 6. Notice on these doubling and half-lives, if it's doubling, what always ends up being in the parentheses here? A 2. And that makes sense because you're doubling, you're multiplying by 2. Okay. By what factor does the population increase in 24 hours? When we say what factor, a factor is how much you're multiplying by the original. So if I had this formula, right, and I wanted to know how many zombies are there after 24 hours, then I would plug in 24 for T, right? Well, what am I multiplying? I'm multiplying the original by all of that. That is the factor. So 2 to the 24 over 6 power. Well, what's 24 divided by 6? That's 4. So 2 to the 4th, what is that? 16. So it increases by a factor of 16 in 24 hours. And what is the population after 1 week? Well, use that same formula. To the T over 6. What's my T? Well, 1 week is 7 days, but there's 24 hours in a day. That ends up being 168 hours. So we need to plug in 168 for T, because my T needs to be in hours. And I end up with a lot of zombies. 805,306,368. So these zombies sure do multiply, I tell you. So there you go. Let's do another one here. We got one with rabbits. Population of rabbits commonly comes up when you talk about this exponential growth. So what is the doubling time? Well, let's see here. A community of rabbits begins with an initial population of 100 and grows 7% per month. So they didn't tell us, so I got to use that formula. Log of 2 over log of 1 plus 0.07. And the doubling time, if you work that out, 10.24. 10.24 what? Well, my percent was 7% per month, so the doubling time is months. Write an equation modeling the population. So Q equals 100 rabbits initially. 1 plus, well, this is nice. They gave us the percent rate, and so I can just do this. All right. So subtle difference there. I hope you caught this. Back here with the zombies, did they tell us the percent that this thing is increasing? No, they told us the doubling time. So since they told us a doubling time, that got put into the power. Okay? On this problem, they didn't tell us doubling time. They told us the percent. And so we can just use the standard model here. All right. So by what factor does the population increase in 18 months? Remember, the factor is this part. And if it's 18 months, I'd throw in an 18 for t. So 1.07 to the 18th power. And that is 3.38. And what is the population after 3 years? Well, my t is in what? T is 7% per month, so t is months. So 3 years is 3 years times 12 months a year. That's 36 months. So 100 times 1.07 to the 36th power. And that is going to give us 1,142.39 rabbits. Let's do another one, half-life time. And this is exponential decay or half-life. All right. And this is very common. So carbon-14 is used to carbon date decaying remains. So like when they dig up the dinosaurs and they say, oh, this dinosaur is this old, that's called carbon dating. Okay. And the way they do that is carbon-14 is a very stable chemical atom, if you will, and it very accurately decays with a half-life time of 5,730 years, like they say here. So knowing that, we can use that to model carbon and model how old this thing could be. So write an equation modeling the amount of carbon in the object. Well, before it died, it had 100% of its carbon. Okay? So, and it's a half-life time. Half-life, and so half is 50%. Okay? Or half-life is a decrease of 50%. So decrease 50%. So in our equation, that would be 1 minus 0.5, which ends up being 0.5 down here. To the t, but this decrease happens every 5,730 years. So I need to adjust my t value to match that. Okay? So again, we don't have a percent here. They gave us a half-life time. And so you have to use that half-life time to adjust your t value. So using guess and check, if a bone has 10% of its original carbon-14 left, how old is the bone? Well, we would guess t values until we got a Q of 10. And I'll let you guess and check on that, but it turns out if you guess, it's a pretty big number, 57,103.9, if you will, years. So, or 57,104. So if you were guessing and checking, you would just keep plugging t values until you got an answer of 10, and 57,104 would do that. So in other words, if they found some bone that had 10% of its carbon left, that's 57,104 years old. So that's kind of how carbon dating works. All right. Let's go ahead and skip this one. Let's get to the review here. So the review. So this is both sections together, linear and exponential. So on the test coming up, you're not going to know which one's which. So let's practice kind of determining that. So the price of milk is increasing by 3 cents per week. So are you adding 3 cents per week, or are you multiplying by... yeah, I'm adding. If you're adding, that's linear. So if the price of milk is $3.65 today, what will it be in 5 weeks? Well, if it's linear, initial amount plus the rate. 3 cents is 0.03, right? $0.03. Times t, and here t is weeks. 3% per 3 cents per week. So there it is. 3.65 plus 0.03. 5 weeks later. Looks like my milk's going to cost me a big whopping $3.80 now. Okay, so that's the linear model, going back and doing that. How about this? The price of a house is increasing by 2% per year. If you ever see a percent, you should think exponential. Okay. So the price is $175,000 today. What will it be in 15 years? So exponential. 1 plus what? 0.02 to the t. And this is 2% per year, so t is in years. That's good. So we'll plug in 1.02 to the 15th power. And if you do that, you get $235,527. And so I can model that with exponential growth. You buy a car for $15,500. It depreciates 12% per year. How much is the car worth after 6 years? Again, 12%. That is exponential. So exponential. Initial amount, $15,500. Depreciates, goes down 12% per year. So 15,500 times 0.88 to the 6th power, because this is after 6 years. And you get 7,198.26 if we round to the nearest cent. So after 6 years, my car is only worth that much. All right. The number of students at DMACC doubles every 16 years. What is the population in 2030 if it was 18,000 in the year 2000? So doubles, that is exponential. So initial amount, well, we know it's 18,000 in the year 2000. Doubling is times 2. But we don't have a percent, so remember, if you don't have a percent and they give you a doubling time, you got to use that doubling time to adjust your t value. And t, by the way, when was 18,000? In the year 2000. So t is years since 18,000, or years since 2000. So 18,000 times 2 to the t in 2030, that's 30 years after the year 2000. If you're going to type that whole thing in your calculator, make sure that whole power is in parentheses. And if we do that, what do we get? $66,024.30. Oh, this isn't dollars, this is people. So, yeah, this is a model. Of course, you can't have 0.3 people, but it's a model, it's a prediction, so it's not 100% accurate. So, according to this, 66,000 in the year 2030. Last example, inflation with salary. So we all know that there's inflation out there. Every year, a dollar can buy you less and less stuff, if you will. So let's say you earn $30,000 per year, which equates to $2,500 per month. If inflation averages about 3% per year, what do you need to make per month 40 years from now to have the same standard of living? So in other words, because of inflation, what do you have to make so that you basically make the same amount as you make now? Well, that's exponential, percent. So you make $2,500 per month right now. 1 plus 0.03 to the t. And this is a percent, so we can just go ahead and throw this in here. Because it's a percent, the percent is per year, so I don't have to adjust my t value. And so 2,500 times 1.03, 40 years later, throw that in, and $8,155.09 per month. So due from inflation, if inflation is an average of 3% per year, which historically that's about right, in 40 years you'd need to make $8,155 just to have the same standard of living. So I hope you keep getting raises. I hope I keep getting raises. All right. I hope this chapter sunk in. How about that? So there it is. That's the end of the chapter. So linear and exponential. We use these things to model data, help us predict things, make future decisions, things like that.